Complete search algorithm for combinations of coins. The problem is similar to coin change problem, but a little different. The problem is stated as, you have a collection of coins, and you know the values of the coins and the quantity of each type of coin in it. You want to know how many distinct sums you can make from non-empty groupings of these coins. So for example, if coins equals 1, 2, 3, and quantity equals 1, 2, 2, there are 11 possible sums, basically all numbers from 1 to 11. The length of the array coins can only go up to 20, but a quantity, x, can go up to 10 to the power of 5. What would be a possible algorithm solution that is efficient? Gathering all possible combinations of such a large quantity will take forever. Is there a mathematical formula that can determine the answer? I don't see how that it will work, especially it wants distinct sums. I was thinking of generating an array based on the coins and its quantity. Basically, it's multiple. Then have to select one or none from each of the arrays. I can't seem to think of a good algorithm to perform that though. Doing nested loop might be too slow since there could be 20 different coins and each coin could have a large quantity. Another possible solution is looping through 1 to maximum, where maximum is the sum of all coins times its associated quantity. But the problem would be in determining if there exists a subset that will be equal to that number. I know there is a dynamic programming algorithm, subset sum, to determine if there exists a subset that will add up to a certain value, but what would be the array?
Don't gather all the combinations, just the sums. Your set of sums starts with 0. Cycle through the coins, one at a time. For each coin, iterate through its quantity, adding that multiple to each item of the set. Set at each of these sums to the set. For example, let's take that original case, coins equals 1, 2, 3, quant equals 1, 2, 2. Walking through this. Next coin. Final coin. Remove 0 from the set, since we're not interested in that sum, and take the size of the remaining set. 11 is your answer. Is that enough to let you turn this into an algorithm? I'll leave the various efficiencies up to you.
Here's a concise brute force solution, Python 3. Then, example. Eliminating duplicates along the way. This variation is functionally equivalent to some other answers, it's just showing how to do it as a variation of the brute force way. In fact, if you squint just right, winky face, you can view it as one way of implementing at user 2357112's polynomial multiplication idea, where multiplication has been redefined just to keep track of is a term with this exponent present or not. Yes, if and only if the exponent is in the sum set. Then the outer loop is multiplying the polynomial so far by the polynomial corresponding to the current value, count, pair, and the multiplication by the x *** 0 term is implicit in the equals union. Although, it's easier to understand if you skip that explanation, winky face.
I was going to put up a solution using generating functions, but then you added. It is guaranteed that quantity 0 plus 1, asterisk, quantity 1 plus 1, asterisk, asterisk, quantity dot length 1 plus 1 equals 10 to the power of 6. In that case, just brute force it. Go through every possible set of coins, compute the sum, and use a set to find how many unique sums you get. 10 to the power of 6 possibilities is trivial. As for the generating function solution, we can represent the sums possible with a quantity q of coins of value v through the polynomial, where a term with exponent n means a sum of value n can be achieved. If we then multiply two polynomials, for example, the presence of a term with exponent n in the product means that a sum of value n can be achieved by combining the coins corresponding to the input polynomials. Efficiency then comes down to how we multiply polynomials. If we use dicts or sets to efficiently look up terms by exponent, we can win over brute force by combining like terms to eliminate some of the redundant work brute force does. We can discard the coefficients, since we don't need them. Advanced polynomial multiplication algorithms based on a number theoretic transform may give further savings in some cases.
Bug fix. Your original solution is fine, except that you need to iterate in reverse order to avoid being able to keep adding the same coin multiple times. Simply change the inner loop to more efficient solution. You can also reduce the complexity by taking advantage of the multiple coins with the same value by scanning up each possible remainder in turn. This will have complexity O maximum asterisk coins instead of O maximum asterisk coins asterisk quantity.
If you want to support the channel, please consider liking and subscribing.